All right. So this is going to be our lecture for week 8, right? So we're just having one lecture this week because the Tuesday class was canceled. Right? And so today's lecture, we're going to finish up our thermodynamics, and then we're moving on into chapter 7, the kind of atomic structure or the electronic structure of the atom. Right? So this is your warm-up question. Sorry, I apparently already gave you the answer. So why don't you go ahead and take a moment, see if you can get that same answer. You can go ahead and solve this. Now, when I do these videos, I'm just going to get to the questions. I'm going to give you a moment so you can pause the video, and then I'm going to start solving them, right? So when you're watching them at home, pause the video so that way you get some moment so you can practice solving it before I get into it. So when we get into this, when we're looking over here, we can see that they're talking about Hess's law. Right? Now, Hess's law means that we're going to use our two reactions here. We're going to look at their delta H's. We're going to try to rearrange these two reactions so that they look like the one at the bottom. So what I recommend is look for things that are unique. So like this NOCl, that's a unique molecule. We only have it in this one reaction, reaction number 2. And we can see that we need it over here. Right? So that tells us two things. One is that we're going to need to flip this reaction. And when we flip that reaction, that means that we need to make this a positive sign. Right? We need to flip the sign. And we know that we need to flip it because that NOCl, it needs to be a reactant and not a product like we have in our current situation. Once we flip that, we can also see that we need 2 of them. We need 2 NOCl. So if we need 2 of this, then we need to multiply that whole thing by 2. And then we can look at that top part. Now in this top part, we don't have any nitrogen monoxide, so that's not our unique part. But what we do have is our nitrogen. So we're looking at these N2s and this O2. And we can see that we also need those to be products instead of reactants. Sorry about that. Apparently, my wrist likes to draw. So that means that we need to flip this one as well. That means that our sign needs to flip because we're going to do the reverse of that reaction. And then we also need to multiply this one by 2. So once we do all of that, we can add the new delta H's up together, and that's going to give us the delta H of our reaction. So we're going to 2 times negative 90.3 plus 2 times 38.6, and that's how we get that 103.4 kilojoules. And so that's how we find that delta H. So we found our delta H through a couple different ways, right? This is the one using Hess's law, where we already have the delta H's for the reactions, and we have to manipulate them. We also found the delta H for the reaction, where we add up our heats of formations of our products minus the heats of formations of our reactants. Right? And so that's another way for us to do it. Right? Today we're going to talk about a third one, and that third way is called bond enthalpy. And so bond enthalpy, remember that enthalpy is that H, means that instead of finding it based off of our molecules, we're going to find it based off of the bonds that form between those molecules. So each bond is actually an attractive force. So there's some force that's there holding them together. And so for us to find their enthalpies, we can think about breaking up all of those bonds between the atoms to separate those molecules apart. And then we can think about reforming them in another configuration. And so average bond enthalpies, they look at several different molecules, several different connections of that carbon to hydrogen bond, several different connections of that oxygen to hydrogen, and then they give us an average amount for them. And so you would get a table that looks kind of like this. And so the important part to know about average bond enthalpies is this is the energy required to break the bond. So we'll always see them as positive because we always need to add in some energy in order to break that bond. Now, different bonds have different amounts of energies. And so we do see that change there. And so the way that you find the enthalpy for the reaction is you add up all of the bonds that you're going to break and you subtract all of the bonds that you're going to form. I guess that should be FORMED. Right? Now, when you do that, just remember that this seems a little bit backwards in some ways, because when we think about bonds broken, we're really looking at the bonds in our reactants, which is different than we think about bonds formed, because these are our bonds in our products. And so it feels backwards, and that's because when you make bonds, you release energy. Let's erase up. When you break bonds, you put in energy. And so that's why they can be a little bit backwards. So here's another practice one. So go ahead and look at this one. This time we're comparing a chlorine molecule versus two separate chlorine atoms. So we want to know what the difference is. Right? And so they talk about that individual atoms are always more stable by 242 kilojoules, which is the bond dissociation energy. That stands for the amount of energy to break the bond between the two chlorines. To transform a chlorine molecule into two separate ones, we have to break one, and therefore the CO2 molecule will always have a lower energy and be more stable. And so we're trying to look at those differences. So what we're looking for is we're trying to see, well, do we have more energy as a molecule or more energy individually? And so if it takes us energy to break that bond, we'll have to put that energy inside. And so if we're putting that energy inside, our products are always going to be a higher energy than our reactants. And so separately, those atoms are always going to have more energy and be less stable than our chlorine molecule. And so that's how we get to B. And so all together, when we're looking at our energies and our enthalpies for that process, remember that if you require more energy to break it than you get back, your net change is going to be an input of energy. You're going to be an endothermic process. If you release more energy when you make your products than you use to break it, then you're going to be an exothermic process. And so you can kind of see how your bond enthalpies help us give us some information about our enthalpy of our reaction, and kind of like whether we're going to release heat or consume heat based on our process. And so this is just a visual diagram where we can kind of look through and we can see whether we're adding or breaking our bonds. And so you can kind of think that whenever you're doing bond enthalpies, you're really trying to break all of those bonds. You're separating them all the way out, and then you're reforming them in that new collection, right? So you can kind of see that we break this one bond here and this bond here, right? We get them as individuals up on the top, and then that gives us space for us to reform this bond here and form this new bond over there. And so our delta H of our reaction is the same as us breaking that bond and reforming those new bonds. And so as an example, this one here, whenever we do our enthalpies of our reaction, right, we want to remember that just as we did with Hess's law, this is an extensive property. So the more of it we do, then the larger that value is going to be. The less of it we do, the smaller that value can be. Right? And so it does vary with how many times we do the reaction. Right? And then by definition, when they write it over here for that, that's to do one set of this reaction. So that's 1 mole of this C3H8, that's 5 moles of this O2, makes 3 moles of the CO2, 4 moles of this H2O. So you can kind of imagine that 1 mole of C3H8 will release that much energy, or 5 moles of O2 will release that much energy, depending on our process. And so that's going to be it for our enthalpies. The last part about heat that we want to talk about is going to be something called latent heat. And this part is looking a little bit about what's happening during the phase change, right? So Enthalpies, this is all for reactions. Latent heat is kind of like us elaborating a little bit more on calorimetry in case we have to go through a phase change when we're doing calorimetry. So latent heat is really tied in with the amount of energy absorbed or released during the phase change. Because what's happening is when you guys get into a phase change, the ice, instead of being heated up, when it gets into this plateau section, it's all of that energy that we're putting in, instead of going to heating up the ice to changing its temperature, it's actually going into breaking up the bonds that hold it as a solid, those intermolecular forces. Right? And so instead, we're putting in energy to turn it from being an ice to water. We turn it from a solid to a liquid, and so that takes energy. So during that period of time, our temperature actually stays very stable. It's why when we have ice water, as long as there's ice in that water, we generally stay around the same temperature. It doesn't vary too very much. Whereas if we don't have ice in that water, then we start to see it really start to rise in its temperature. Now, this first transition, we should know that that's melting, right? As we go from a solid to a liquid. And this second one, as we go from a liquid to a gas, that's going to be for water. And so that's going to be our evaporation or vaporization as we go into steam. Now, sometimes when we talk about these, you'll only see one side of it. And so we want to know that they're related. So when we talk about evaporation or condensation, those are the same process. They're the same heat. One is just in one direction, the other is in the other. Same with melting and fusion. So when we talk about the delta H of fusion, that's the same as the delta H of melting, except one is going to be the positive version, one is going to be the negative, right? And so that section, those plateaus, those are our latent heats. And so that's what that means. Sometimes they call them the hidden heats. They're normally given in joules per gram. And the reason why they get their name as the hidden heat is that this is when heat is going in and we won't see a temperature change. Instead, that energy is going for it changing its state. And so sometimes they call that the hidden heat loss, or the hidden heat. So I've gone through, this is the same diagram. We're just giving them some numbers so that way we can kind of use this when we get into the next slide when we talk about solving them. And so for A to B, this is going to be section 1, and this is when we're only in ice, right? So all of this section is when we just have ice. And so A to B, that section is us warming that ice. And so we would find the heat that it requires through this equation, right? It's going to be the heat that we need to raise that temperature. Now this is going to be the mass of our ice, and this is the change that it feels. The only difference is that this C is going to be that for ice, not water. So it gets a different specific heat capacity. Let me clear these up. All right. Now when we get into number 2, right, section 2 is going to be our next part when we go from B to C. And B to C is when we're not just warming the ice, but we're really melting the ice. We're changing it from being a solid to a liquid. So this is when we're going from ice to water. And so that is just given by this enthalpy of fusion here up on top and the mass. So we don't have any temperature change because it all stays at the same temperature, but this is the energy that required to melt it. In this case, it's going to have a heat of fusion of a positive or a negative 333 joules per gram. And so it depends on which direction we're going. Now, when you think about it, you'll be able to know whether it should be positive or negative. You just want to think if it takes energy or releases energy. So when you are melting something, it's going to take energy. And so the delta H of fusion is always going to be the positive value. Right? Our solid should have more energy inside of it than our liquid. And so we are going to heat it. We're going to put in energy as we go from that solid to that liquid because we have to break those bonds. Or not bonds, those attractive forces is a better term. Right? And so that's how we're going to solve section number 2. Section number 3, right? This one, now we only have water. And so we're going to find that this is just us warming water. And so we should use that same equation. We're in that same state. The only difference is that we have the heat capacity for the water. So our usual 4.184. take a moment. I want you to think about what section 4 is going to be. This is when we're going from D to E. So think about what you think that would be. And if you thought that that should be us boiling the water, right? So the vaporization from liquid to a gas, then you're totally correct. And so we call that vaporization. And so you can see that we have that delta H of that vaporization. And so once again, we are putting in that energy. And so it's going to be positive over here with our vaporization, whereas condensation is going to be the negative, in the same way that melting would be the negative. And then that last section, section number 5, that's when we're working with steam. And so this is when we're heating steam. And so it gets its own heat capacity. And so this is how you would do a heating curve for water, right? Every element or every molecule gets its own heating curve. And so this is an example for water. And so I want you to take a moment, write down these values because we are going to need them in our next slide, right? So in the next one, we're going to work with them to kind of solve this problem to see how everything's connected. So we're going to solve this first one. I'm going to put answers for 2 and 3, so that way you guys can practice them. And then if you need to, we can always walk through and solve them again. And so what we want to do is now we are looking for a sample, right? And so I'm going to use this diagram up here at the top corner, so that way we can think about where we're starting and where we're going, right? So we're going to use red for our starting sample, and then we're going to use blue for the water. So we're starting with a sample of ice, and we're starting at 25 degrees Celsius. So we're starting way down here. Right? Now our water, it's starting somewhere else. Our water is starting at 85 degrees Celsius. So up here. And so we want to find the final temperature of the mixture. And, or sorry, if the final temperature of the mixture is 15 degrees Celsius. So that means that we are meeting, we're going to use a purple for that because that's blue and red mixed together, at 15 degrees Celsius right here. So if we're trying to get here at the end, right, they want to know what the mass of the ice is. So we have 2 options of where this is going to go. We have our water side. Now our water side is a little bit easy because our water it's staying in the same state. So it starts off as water. It's going to end as water. And so we can find that entire change of the water using the equation mc delta T. And we know M, we know C. We're going to be able to find the delta T because we have the initial and the final. Right? So from our water side, it's pretty straightforward. The harder part is going to be from the ice. Because for our ice, we have 2 sections. We have section number 1, right? As we heat the ice. We have section number 2 as the ice melts. And then we have section number 3 as we heat that melted ice, right? So that water now to its final temperature, right? And each time we don't know what the mass is. So we're going to walk through that. So I'm going to go over to my whiteboard. And we're going to look at that part. So I'm going to start with the easy part first, because why not? So our easy part is going to be our water. Excuse me. So we know that the Q of water, right? So this is our sample that we started with. It's going to be a mass of 75 grams, a heat capacity of 4.184 joules per gram degrees Celsius. And we're going through a temperature change of, well, don't have enough space there, so I'm going to get rid of these units for now. And we're going from a temperature change. We start with we're ending at 15. We're starting at 85 for a degree Celsius. So when we look at that Q of that water, that's going to be our 75 grams times 4.184 joules, grams, degrees Celsius. And we had a temperature change of negative 70 degrees Celsius. So now as we walk through that, we can see that our Q of our water is a negative 21,966. And that's going to be in joules, right? Because our grams and our grams are cancel, our degrees Celsius and our degrees Celsius will cancel. Now, when we think about that, if we go back and we look at our diagram, we knew that the water lost all of that heat, and that's going to be equal to the heat that's gained by the ice. So we know that the Q of our water is equal to the Q of our ice, except for one change, and that should be the negative sign. Right? So we're going to flip it over to figure out how much heat our ice gained. Now, we said that the heat that the ice gained really came into three parts. So part one, part two, and part three. Right? We have the heating of the ice. We have the melting of the ice. And then we have the heating of the melted ice. Sorry, apparently my thumb really likes to write, okay? So what we need to do now is we need to break down each of these parts and we need to fit in their equations. So we know that Q1 is going to be the mass of the ice, the heat capacity of the ice, and it's going from a temperature change of 0 degrees Celsius, where it's going to end up, and it's starting from one of minus 25. Now, we don't know what the mass of that ice is, but we do know that the CS should be 2.077 joules, grams, degrees Celsius. We do know that its change should be 25 degrees Celsius. So we can stand in that the Q1 for this should be 2.077 times 25. Joules per gram. We can do the same thing for our Q2. Now our Q2 is going to be the mass of the ice, and then is what we need to melt it. So when we think about melting that ice, we have the delta H of fusion. And so we want to think, should we be using the positive or the negative? And it should be the positive. So we can leave that there. Q3 is going to be the mass of the ice, the heat capacity of the ice now that it's a water, so 4.184. And then we're doing that temperature change. So it's going from 0 degrees Celsius to 15. And so we can see that our Q3 is the mass of the ice, and then that's 4.184 times 15. So we get that 62.76 joules per gram. So we want to go ahead and consolidate those. We want to consolidate them together so we can get one expression. So Q of ice is equal to the mass of ice times, and then I'm going to go ahead and I'm going to add in this 51.925. 51.925, the 333 and this 62.76, we'll add them all together. So that's going to come out to the Q of our ice is the mass. That's terrible. The mass of our ice times (444) or 447 joules per gram. And so now we have this expression down here that connects them. So we knew that our water was negative 21,966 joules. And we know that our Q of our ice is the negative value of that. We can now use our expression for our Q of our ice from up here. We can put that in there. We can set them equal to each other. And so our M of our ice becomes 21,966 divided by 447. We get 49.07 grams, 49.1 grams. And so if we take that, we go back to our slide, we find out that our answer is 49.1 grams. So that's how you would solve that. So think about what options you have, and you can work on number 2 and number 3. I do have answers for them, so you can always go ahead and use that when you guys are getting there. And so this is what those two values are going to look like. And so that's how you do the heating curve of water, right, as you guys go through your latent heats. And that's pretty much going to be the end of our thermal chemistry. From there, we're going to move into our chapter 7. And so we're going to start with the kind of the electronic structure of the atom, right? And so we'll talk about why we need to do that. And so we're going to be looking at that at our next part. All right, so this is chapter 7. Oh, that's not a pen. Sorry, give me a second. I apparently canceled my share. There we go. All right. And so we should be looking at this screen. There we go. All right. So this is for chapter 7. Now, what's different about chapter 7 is that we've already talked a little bit about the atom, right? We've talked about the protons, neutrons, electrons. We've talked about nucleuses, right? We've also even talked about periodic trends. But what we're getting into is something called quantum mechanics, right? And a lot of times that seems very scary. Right? But the reason why it's important is that so far our periodic trends tells us what is going to happen, kind of like what properties we see, but doesn't really explain why. And so we have to get into the quantum mechanics side so that way we know why things happen, not just what happens. It's kind of like driving a car. You know what happens when you turn right or turn left, but why might not be there, right? You might not understand exactly how you did, how your internal combustion engine works, right? You might not know exactly how the wheel is connected to your tires, right? But we know what is happening, we don't know necessarily why. And so for us and our class, we're going to be looking at why, which is why we have to do this quantum mechanics side of things. And so quantum mechanical theory, it starts to explain the behavior of the electrons in the atoms. And so it talks about them existing in these orbitals and where they exist. It's also going to give us something that's very useful. It's called an electron configuration. And we're going to use that next week when we start to identify atoms and talk about where all of their electrons are located. But before we can get into all this stuff about the electrons, we're first going to talk about just particles in general. And so we're going to talk about electromagnetic radiation. Right? Now, what's interesting about it is that all of the electronic structure of an atom, it's based on this type of radiation. And so it's type of a material, right? And so what you want to know about them is that they move as waves through space, and they all move at the same speed, the speed of light. So it doesn't matter whether you're an electron or a photon, right? All of the electromagnetic radiations that we're going to talk about, they all move at the same speed and that's the speed of light. Now there's a couple of terms that we want to be interested in. The first one is going to be wavelength. Now wavelength is just like what it sees in this picture. Right? It's the distance, the physical distance inside that pattern, that radiation, between the same peaks, right? So peak to peak or trough to trough, wavelength is the distance that it needs to be before they see them, the corresponding point again. You can also talk about them in terms of frequency. Frequency is the number of waves that pass, right? So if we were to look at this, this was kind of like a section of 1 second, this wavelength for A would be this distance, and it would have a frequency of 1, 2, because we saw it twice inside that span of a second. If we look down here at B, B is different. It has a smaller wavelength, right? Not as big of a distance before it repeats. And instead of only seeing 2 peaks in a second, we saw 1, 2, 3, 4. And so its frequency is 4 times per second versus the 2 times per second of part A. So there's a combination between there. There's a relationship. Because if everything travels at the same speed, which is c, and that has a value, 3.00 times 10 to the 8 meters per second. You also can notice on the back of your equation sheet, you have the speed of light in there as well, 2.998 times 10 to the 8 meters per second. Right? Then if they're all traveling at that same speed, then the frequency that we see them is related to their wavelength, right? By that equation down there, which is why when we shorten the wavelength, we increase the frequency. If we lengthen the wavelength, we're going to decrease the frequency. So they're inversely related to each other. When one goes up, the other goes down. So the reason why we're interested in electromagnetic radiation is all of this is electromagnetic radiation. It's all the same thing, just at different wavelengths and different frequencies. So when we talk about the light that you see, that's going to be what we refer to as this visible region here. So the colors of the rainbow, they form because they're just different wavelengths of that light, that electromagnetic radiation. And they just happen to have a wavelength in this nanometer scale. If we make them a little bit shorter, then that's where we get into things like our ultraviolet radiation here. And so that's where you get a sunburn, right, from the UV rays. That's what they're talking about. And so they're a little bit shorter in their wavelength, a little bit higher in their frequency. That's the same thing for X-rays or even to our gamma rays, right? Those are just more energetic forms of electromagnetic radiation. On the other side, if we go longer than the visible region, we get into that infrared light. And so that's where we're getting into things like heat, right? We can also be talking about things like microwaves. So when we call it a microwave oven, it's really because it's using radiation, electromagnetic radiation, but just with a wavelength in this range. And then larger than that are things like radio frequency, wireless internet, TV, right? All of those things are just different types of this electromagnetic radiation. And so when we look at them, their wavelength and their frequency is really tied into certain types. So whether we're doing radio waves, which are quite long, they can be on the kilometer scale, or we're doing television waves or we're doing microwaves, they're all tied in with a certain wavelength area. Right? And so that's what we're interested in. Now we really want to pay special attention to nanometers because this is what we use a lot for this class because we solve things a lot in the visible light spectra. Okay? So we want to make sure that we can pay attention to that part. And so here's a practice problem. Right? So we're talking about these waves down here. So when it's talking about wavelength A, it's talking about this picture here. When it's talking about wavelength B, it's talking about that one. And so those are to scale, so you can look at their relative sizes. So this is the speed of light. And so if we're comparing them, wavelength A, this is 2.0 meters, and it's got a frequency of 1.5 times 10 to the 8 cycles. So when we compare it with frequency of B, it seems like this is 1, 2, this is 1, 2, 3, 4. So we must have twice as high of a frequency. So that means that we have to be 3.0 times 10 to the 8 cycles per second. And now we just want to think, well, if our frequency doubled, how did our wavelength change? Right? Did it go down by half or did it go down by 4 times, right, or a quarter of it? And so when we look at this one, if our frequency has doubled, then our wavelength must have gone down 1/2 in order for us to keep that same C. So you could plug in the values into the equation and you can solve it mathematically, or you can look at those relationships. But that's how we get to A as being our answer. First, part number 2, we're going to go ahead and look at the wavelength of a green light at a traffic signal. And so it's at 522 nanometers. So we want to find that frequency. So we know that C is equal to our frequency times our wavelength. Now we know our C is in meters per second. Our frequency is 1/second. And so we want to make sure that we get those wavelengths into meters in order for this to work. So once we've set up that equation correctly, we can manipulate it over to V equals C over lambda, right? So that was C equals V lambda. And so we just migrated our V or our lambda over, right, to solve for our frequency. And then down here, we need to change our nanometers into meters. So we need to multiply it. We get 522 times 10 to the 9, which is that in our meters. So now we're all set, our units line up. We can then plug that in. We have 3 times 10 to the 8, 3 times 10 to the 7. And so our answer is going to be 5.75 times 10 to the 14 cycles per second. And so hertz is another way for us to talk about that. Hertz just means per second. Right? So all of those things is what hertz stand for. So when you're talking about your wireless cell phone being at 2.4 megahertz, that's the frequency that operates at. Or when you talk about your Wi-Fi internet being 5 gigahertz, right? Then it's talking about what band of the wavelength, the electromagnetic radiation spectrum that it's using, right? And so different ones have different energies, and that's how we can tell the difference between the different uses. So that's our first equation. The second equation is that, well, for our electrons, we realize that while they have wave-like character, we wanted to know why for our electrons we see these wave-like characters, but for the bigger things we don't. Right? When you throw a baseball, it doesn't seem to move like a wave. It doesn't travel through the air going up and down. It really just travels looking like that. And so de Broglie, he decided that, well, maybe it's related to the momentum of a particle. And so they give us this equation here. And so what this is looking at is this is our mass. And instead of being our frequency, this is going to be our velocity. And so pretty much the heavier you are and the faster you're going, then the less like a wave we're going to see. right? It's going to become so big that your wavelength is going to become very, very, the bigger this term at the bottom becomes, then the smaller your wavelength is going to be. And so we start not being able to see the difference. This one up here is called Planck's constant. And that's going to be our connection between them. So we can kind of combine this in order to do a practice problem where we're going to try to look at an electron, and we're going to look at what the wavelength it would be for a certain velocity. Now, we won't do this so often, but sometimes I think that this is a very useful concept, so you can kind of see why this matters for such small particles, but doesn't matter for our bigger ones. And so if we wanted to solve this, we're basically asking to find that lambda. So we have to rearrange that equation. And so we just need to pull in those pieces that we need. We know that we have the velocity. We know that h is 6.626 times 10 to the negative 34 joules seconds. And so the one thing that we do need to stand in is that, and so we just need to look up the mass of an electron. And so that one we're going to be able to find in just a second here. Now this is an important part. Remember that a joule is defined as moving 1 kilogram, 1 meter squared, second squared. And so we can use this once we get our mass into our kilograms. And so that's what's going on here. So this was our mass of our electron. Right. You can see it's really small, and we've just adjusted it to be in kilograms. We plug in those other values, we line them all up, we solve for our velocity. And so de Broglie basically helps us explain why our electrons move like waves, but we don't necessarily see it with somewhere else. Now, the last equation I want you to know is Planck's equation here. And so this is for a photon, and it's tying into the energy of a photon. Right? So this h is the same h, it's Planck's constant, just like what we just used. Your speed of light is still that c, and now we're using our frequency. Because what we've done is that Planck said that the energy of a photon is kind of related to how often we see the frequency, how often it shows up in its peaks. And so we've kind of combined two equations, right? We've used c is lambda v, we solve for v, and that's how we're able to change this equation into that one. And so that's how we can connect those two things. Now, this is an important part, right? While we're using these energies, right, and these equations, we're going to be able to use it to help us explain the behavior of electrons. Now, it doesn't explain everything. There's 3 different parts that aren't explained by the wave side of things for the electrons. They're covered here. We'll talk a little bit more about them a little bit later. It doesn't tell us why when we heat certain objects, like they glow, they become really bright and they give off light. It doesn't explain why when we shine light onto metal surfaces that we get the photoelectric effect or electrons get kicked off of it. And it doesn't explain why we get certain lights emitted from gas atoms, right? So that's not explained by the waves, but it does give us a lot of other pieces about how that puts together. And if you wanted to see one, this is an example of how when we increase the temperature, right? So when we heat a nail, that nail starts to give off light. And so we're going to talk about those a little bit later. But what we do know is our current model of the atom looks like this. We have a tiny nucleus that has all of the mass of the atom, or pretty much all of it, right? Because it's got all of the protons, and it's also got the neutrons. So it's going to be all positively charged because it's got protons in there. The electrons, on the other hand, they move around that empty space. So the problem with this model is when we thought about it, well, we'd have that nucleus, we'd have those electrons traveling around it. But electrons are in motion, right? They're moving around in those orbits. And so if it's moving around in that orbit, what classical physics says is that, well, if we had a nucleus and we had an electron, every time that electron turns, it should lose some energy. So instead of making a perfect connection, it should actually come in a little bit more and a little bit more each time as it loses energy, and it can't keep quite as far away because it's not going as fast. So that eventually that attractive force should pull that electron into the middle. And then not only would they eventually collapse because it would crash into the nucleus, but that whole time our atoms are going to glow because they're releasing heat. But that's not true. That's not what we saw. And so what that means is that we have to introduce another type of atom, another model. And so we built on it. And so basically what Bohr recommended was, he said, okay, maybe our structure was relatively the same, but the difference is going to be that instead of it being a continuous spectrum where electrons can be like a ramp, we're going to say that the energy of the atom is restricted into these what we call quantized, right? So that means that the amount of energy in the atom is related to the electron's position, but they can only have very specific amounts. So instead of being a ramp where we can have energies all the way down, it's really more like staircase, where you're either on the top of the stair or you're on the next stair, but you can't be in between. And so that's what he meant when he said that we're going to have quantized energy inside of the atom, is we're going to have these discrete areas, these discrete energies that an electron can exist at. All of the other times, we're going to say that it can't. And so to get an idea of quantized or not, right, we're going to talk about two instruments. We're going to talk about a piano, we're going to talk about a violin. And so I want you to think about each of them. Is a piano going to be something that is quantized, or is it going to be something continuous? Versus a violin, is that something that's quantized or something that's continuous? And so when you think about it, you kind of have to think about how you play them, right? So piano is played with keys. Now a key means that you can push down your key and it will strike that chord at that one value. Right? But there's the sharps and the flats, but in between those, there's kind of steps, right? So each of those keys is a step. So we can hit the different notes, but we can't necessarily hit between those notes. A violin, on the other hand, is strings, right? And you hold the strings at different points. And so depending on where you hold the string and how far down it is, based on where you're striking, you can get all the different frequencies in between. Right? So a piano, it only has certain notes and you don't have anything in between. Whereas a violin is going to be continuous. We're going to be able to play all of the different frequencies because of how you play the instrument itself. So Bohr's model is like the piano. We have fixed distances that we can be. They're these stationary states. And so the energy of the electron is kind of proportional to its distance away. So it can exist in these rings moving away from the nucleus. So keeping our colors the same, our nucleus is here in the middle. So we have our very first ring. And we'll call that n equals 1. It's the closest one. And so that has one energy. We can then have a second step, n equals 2. Ideally, these would be like circles, but bear with me, I can't draw, right? And they'd have a different energy. And so electrons, what they can do is they can jump between these different rings. Now, a higher energy means that it's farther away. A lower energy means that it's closer to the nucleus. And so when they jump down from a high to a low, So let's draw our electron in here. When it goes down this way, it's going to emit energy, it's going to release that, and that's going to come off as a photon of light. When it goes the other way, from low to high, then it needs to absorb a photon. Photon has to come in order to excite that electron to make it move. Whereas when it goes down, it's going to actually emit that photon. Now, Bohr's model, we've been able to verify because when you look at a single element in its gaseous phase, when we start to heat it up, we can, or sorry, not heat it up, when we start to excite it, we can get these electrons into these higher energy states. And then when they decrease in their energy level, so as they go down, they release these photons. And what we see is instead of seeing the entire spectrum of the rainbow, like we would if it was a continuous one, we see that it only comes out in these lines. And this is called the emission spectra. And this is actually what our lab is going to be about. We're going to look at the different emission spectra of the hydrogen, helium, and I believe mercury lamps. And so we're going to look at those energies associated with it. So Bohr's model is really about that the electrons only are permitted in these allowed energy states. So you can only be in certain states. There's nothing else in between. This way, we don't get that spiral effect. It doesn't spiral down and collapse. We have to stay in those very specific values. Now, what you want to remember is that the higher your energy level, right? So the higher that N value is, the more energy you have. The lower, the less. And it's kind of like the closer you are to the nucleus, the less energy you're going to have because the more stable you are. So it's always going to take you energy to get away from the nucleus. So energy is going to be absorbed by the electron when it goes from low to high, and then it's going to be emitted when it goes from high to low. Now, the lowest energy state is always called the ground state, so that's where they're starting from. And the higher energy state is called the excited one. So when we look at these transitions, this transition right here of this line, it's moving from an excited state of 6 to a ground state of 1. Now, if it goes 6 to 1, it's going to emit a photon. And if it goes from 1 to 6, it's going to absorb. Now, this equation down here, this is going to allow us to predict that change in that energy. But be careful, this value here, this value is only for hydrogen. Different elements will have different values, and so that's what we need to put in there. And you can see on your equation sheet what that looks like. Right? And so you just want to make sure that you're paying attention to those changes. Right. Now, you'll see it written in 2 ways. Sometimes they have final minus initial, sometimes it's initial minus final, and it all depends on the term that you look at. Some of them will give you positive RHs, some of them will give you negative RHs. And so what you want to remember is you have to choose for yourself that a positive delta E means that you're absorbing. And this is your final is higher, greater than your initial. A negative delta E means that you are emitting, and so your final is less than your initial. So keep that in mind as you try to use your equations. If you just pull them offline, sometimes they'll be written in one way, sometimes they'll be written in the other. I prefer mine as my initial minus my final. I find it easier for me to remember. Others prefer final minus initial. So it's up to you, right, how you want to use it. But the one on your equation sheet is going to be how I provide it for your quizzes and your exams. And so this is going to be an example of our emission spectra. You can see here on this slide, we can see a lot of different ones, and each element has a different emission spectra. And so really what they're doing is they can take that light released by the element, we can shine it through a prism to separate them, and we can see it over on this side. So the last part that we're going to kind of get into is something called the uncertainty principle. And so the uncertainty principle means that when we work with something really small, there's kind of a problem that arises, right? And the uncertainty principle was discovered by or theorized by this scientist named Heisenberg, is that we can know the mass or we can know the position of something, and we can know the velocity of something, but it's really hard for us to know both of those things at the same time. Because if you wanted to imagine it, you could take a picture and you would know exactly where something is. But it's really hard for you to tell the speed something's moving at by that picture. It gives you the position, but it doesn't tell you where things are moving. And we can tell the velocity of something by putting up two pieces and letting it move through. But once it's passed through that point, we would know its velocity, but we wouldn't know where it actually is, because it could have continued on, it could have turned left, it could have turned right. We don't really know. So we can know one or the other, or we might be able to make an estimate of both. But we can't know exactly where something is and exactly how fast it's going. Now, this matters a lot more on the quantum level because it's related to Planck's constant. As we get bigger, it doesn't really matter as much because the object's bigger, so the uncertainty that we have in its velocity and its position matter less and less. And so this introduces the kind of like the strange part of quantum mechanics, which is where it varies a lot from our classical. Classical physics allows us to predict what's going to happen, right? It gives us a very definite and predictable future. Now, because we don't know both of those things, its position and its velocity for an electron, we can't really predict exactly what's going to happen. We can only predict where it likely will end up. So let's just do probability as compared to a known fact, right? And so the best that we can ever do with our electrons is we can just give you a region where they should be with high statistical probability, right? And so if you wanted to imagine this with baseball, when you throw a pitch, in classical physics, your ball would look like this, right? In quantum mechanical, really what it is it comes out with this scatter plot, this distribution of where things are going to go. Right? And so we are pretty sure that it's going to end up in that same part 20% of the time. If we widen that circle, it gives us more and more confidence in where it could be. And so quantum mechanics kind of gets into this iffy part, this gray area. And so instead of knowing facts, we know probabilities. We know roughly where things will be inside of a range, right? And so that's what quantum mechanics kind of does. And so when we start talking about our electron clouds, then we're talking about is that there's a probability that our electron is somewhere in that cloud. And so that's what we're going to talk about next week, right? So when we define our orbitals, we're really talking about the probability density that the electron's somewhere in that range. So 90% of the time, it's going to be inside of that. And that's how we get each of those different ones. And so that's what we're going to stop today, right? On next week, we're going to talk a little bit more about electron energies. We'll talk about Schrodinger's equation, and then we'll move forward with our quantum numbers, and then we'll get into the electron configurations as well. Make sure that you keep up with your homework. Make sure you do a little bit of reading. This chapter seems to be a little bit of a struggle in that we deal with some very small numbers. So math-wise, there's a little bit of a struggle. And conceptually, there's a big struggle because we're starting to get into some of the harder parts to imagine. So make sure that if you have questions, ask inside the discussions, work on those worksheets, and we'll move all of that all the way through.